proceed in case everybody is there from the crediting group, or at least some of you can represent them. There was a request to change the exam date from 21st to 26th. So is that okay, or is there some objection to that?
So 28th will be okay.
28th.
26th, I think Rohit is having exam. 26th MDT exam is going on.
I see.
I think Rohit is crediting that course.
Yes. Okay, okay. So 28th you think will be okay with all the people crediting the course? Sure. 26th is 28th, I think, is a Saturday, right?
Sunday.
28th is Sunday. Okay, if that's fine with everybody, that's okay. So today will be the last day of this course as far as the teaching is concerned. I should have brought the course evaluation forms. It will be a long class, 3 hours, so we'll probably have a 5 or 10 minute break in between. Based on the actual content, I will let you know when the break would be. So the first part of today's class, we're going to do something which we did in the previous class for a specialized case. Now for the more general case of a composite beam. If you recollect that we applied it to an isotropic beam, and we showed how the variational asymptotic method led to basically zeroth order approximation and a first order approximation, and what were the differences between that, what were the additional terms, and what was the 1D constitutive law that resulted because of that, the additional terms, their physical meaning, interpretation, etc. Now we'll try to do something similar for the general composite beam. The difference is, one of the main differences is that whereas that was analytically tractable problem, this needs to get into numerical solution more, and typically what is used is the finite element solution. Of course, the one-dimensional beam problem is highly nonlinear coupled, and that is almost always done using 1D finite elements. But this is what I'm talking about is here is the cross-sectional analysis, and that too in this case would be done by using a finite element kind of an implementation. We will not go into the finite element implementation aspect of it, which is already done in the software package called VAPS. But instead we'll go into some of the basic theory governing that and see how that eventually would translate into VAPS without going into the details of the software itself. So before we proceed to this specific example, the more generic example of a composite beam, we'll just summarize what we learned from the previous simpler example for the isotropic beam. So that will give us an idea of what is to come for the general case. So the example of applying VAM was to an isotropic initially curved beam problem. Of course, initial curvature includes the pre-twist as well. The only assumptions in the entire dimensional reduction process were two. One is the strain itself being small because of the material being used, typically having failure strains of the order of 1% or so. And because the cross-sectional geometry is and the overall geometry of the beam is such that the cross-sectional dimensions are small compared to both the length of the beam as well as the initial radii of curvature. So therefore we basically said that A by R squared is small compared to 1. So which means that A by R is typically of the order of 10%, whereas A by R whole squared is of the order of similar order as epsilon hat, which is of the order of 1%, so that 10 power minus 2. So that is the kind of small parameters that we used, and that contains a very wide class of engineering problems in all branches of engineering, in particular in aerospace engineering, where this becomes applicable. And of course the next, we already saw in the previous example, we went from U1D naught, which was a zeroth order approximation, then we went to the so-called U1D subscript Roman 1, which was basically the first order approximation. Theoretically speaking, you could continue doing that. For example, the next approximation would be U1D subscript 2, which is the second order approximation, and the new terms in that case in the energy would be, apart from the leading order terms and the A by R corrections, which we already obtained, there would be an A by R whole squared correction, and so on and so forth, right? So in U1D with respect to its leading terms, and these, if it were to be done, would be associated with large initial curvature and the transverse shear effects, which we did not capture in the previous example. Then to find them would require solving the Euler-Lagrange equations governing VI. So remember that VI was the first order warping. We saw that it was entering into the derivation, but we really didn't need to solve the Euler-Lagrange equations or the governing differential equations for VI. We didn't have to obtain a solution for VI and substitute it, because even without doing that we were able to obtain the A by R correction. So that was something which was beneficial, and therefore we didn't do that. Whereas before we go into the second order approximation, we could get the solution of that VI, and that would help us to get the second order corrections, in other words A by R squared terms as well into the energy. Substitute the warping, which is basically the first order warping, includes the zeroth order approximation and these perturbations, which in this case would have to be solved for. First we would substitute them into the 3D strains, which is the Jean-Monbel-Cauchy strain tensor, which involves the derivatives of this with respect to, in particular, x2 and x3, the cross-sectional coordinates. And then we would basically substitute that gamma ij into the energy to get the asymptotically correct 3D energy. As far as the strain field is concerned, it would then be correct up to the order of epsilon hat A by R. Without doing that, it would not have been correct up to the order of epsilon hat A by R, because some of the strains would have been corrected while the other strains would not have been corrected. We say that something is, a particular field is correct up to a particular asymptotic order only if all components or all measure numbers of that particular field are of the same order of magnitude. Then we say basically that up to that level of correction has been incorporated. Whereas it was not done because of the fact that we did not explicitly determine VI. What I mean will be a little more clear in the next slide. So this is of course the constitutive law that we got in the previous example, the isotropic example, and we said that the non-underlying terms were the zeroth order approximation, the underlying terms were the additions that we got with the first order approximation. And of course, if you go to higher order approximation, the next correction, for example, would involve a by r squared correction in both the axial force stress resultant as well as the bending moment stress resultant. But without finding VI, the analysis allowed the recovery of gamma 1i already up to order of epsilon at A by R, because if you recollect, the gamma 1i, that is the strains associated with the one direction, the axial strain and the two transverse strains, those strains did not contain derivatives of the warping with respect to the cross-sectional coordinates. So it was only in the gamma alpha beta, that is in 2, 2, 3, 3 and 2, 3. And therefore, whereas those were already obtained up to that order, an additional order compared to the leading terms, that is namely an A by R correction was also obtained, you had not yet obtained the correction up to A by R in this because you had not solved for the VIs. But if you did solve for the VIs, then this would also be obtained up to the same order, that is epsilon hat A by R. Now without solving for VI, the 3D stresses sigma ij, which of course will be determined using the 3D strains, because the 3D strains are now obtained once the warping is known, because the expressions for gamma ij are in terms of the warping would be substituted into that. You will go back to the 3D constitutive law and basically get this. In the case of the isotropic material, of course, it's a homogeneous isotropic material that we considered, so then it will be, the EIJKL would also be a fairly simple tensor components that we would have to deal with. But even in a generic case, even when we go to composites, we would see that the 3D recovery would eventually be done for the stresses by using the 3D stress-strain relationship or the constitutive law, which depends purely on the material alone. Now, if we had not solved for VI, which is what was the situation at the end of last class, what would happen with the sigma ij is that because this sigma ij in general depend upon all of the gamma KLs, though some of the gammas are up to order epsilon at A by R and some are not up to that order, they are only up to the leading order. Therefore, in the strains also, the stresses also, you would have the recovery only up to E times epsilon hat. There would be some terms, spurious terms coming because of this, but you cannot say that the stress is accurate up to the order E epsilon hat into A by R, because some of those were absent in being substituted here, and therefore in the recovery of the stresses. So which implies that suppose you're talking about the 1D stress resultants, there are two ways to obtain it. 1D stress resultants can directly be obtained from the 1D strains by using the 1D constitutive law. That is the best way to obtain it. On the other hand, you also know that the 1D stress resultants are related to the 3D stresses as their integrations over the cross section in an appropriate manner. So for example, F1 would be just given by sigma 11 integrated over the cross sectional area, right? So similarly, F2 and F3, and of course M1, M2, M3 are along with the appropriate moment arms about the reference axis. So the 1D stress resultants, if they are calculated in two different ways, they can disagree. The two ways that I talked about, the one which is a more direct way where you already have the 1D strains, degeneralized strains of gamma 11 bar, kappa 1 bar, kappa 2 bar and kappa 3 bar, directly substitute that into the 1D constitutive law to get your F1, M1, M2, M3. But that instead, if you first determine the sigmas using this relationship and then integrate the sigmas to get the F1, M1, M2, M3, these two in general could disagree because of this confusion or mismatch that we just talked about. So if you integrate the 3D stresses, what would happen is you have incomplete A by R corrections because in the stresses these are not correct up to that level, and these only are correct up to that level, and therefore you would have for example certain quantities like F1 for example correct only up to EA epsilon hat, whereas with this constitutive law you can see that it's already correct up to EA epsilon hat into A by R. The next term which is not added is A by R squared. So already what is there is up to A by R. Okay, so that is basically what we are telling. Instead, if you had gone through the stress to get it, you would have only got up to EA times epsilon hat. That is only up to this, right? So similarly, the M3, whereas here it involves up to A by R corrections, it's only the A by R squared and higher order terms which are dropped off. Here, if you had gone to determine that instead by using the 3D stresses and integrating it by multiplying, see M3 is basically the moment about in the 3 direction, which basically means that you're basically talking about this is the thickness direction. So in the case of a strip-like configuration, the M3 moment would basically be like this. So you're talking about sigma 1 into x2. And then integrating that over dA, which is dx2, dx3 in this cross section, and that's how you're basically determining it. If you had determined it in that way, once again you would have had the correction asymptotically correct only up to the classical level, that is basically your EI3, and of course epsilon hat by A, because basically it is a curvature, so it should have a dimension. So basically that 1 by A aspect is coming into it, that is basically the curvature that the bending stiffness multiplies. So in other words, your bending stiffness is correct only up to the classical level and does not involve these higher order terms accurately to the extent that it is necessary. On the other hand, as I said, the direct approach would be to use the constitutive law as is listed in the top of this slide over here. Then you know that both these results would be correct up to the first order of correction, namely the A by R correction would be included both in F1 as well as in M3. So what we saw was an illustration of an analytical application of the variational asymptotic method, and it was possible due to the simple cross-sectional geometry. Remember that we considered basically some planar deformation which was enabled by an appropriate application of the loading as well as the choice of the cross-section such that the deformation would not be out of plane. In other words, there would be no twist, there would be no transverse displacement or bending in the other direction basically. So all those things was possible because of the simple cross-sectional geometry, and of course we applied it to a problem where the material used was isotropic, containing only E's and U's, or equivalently the Lamé parameters. So the material property distribution was simple there. But in a general case, which is what we are going to explore from the following slides, using VAM would be requiring us to have a numerical approach instead of the analytical approach, and therefeur we'll have to discretize the Wi in some way, because Wi is the unknown quantity. If you remember, even in the previous problem, the Euler-Lagrange equations turned out to be nothing but the governing differential equations for W, the partial differential equations that you had for W, and you then determined the solution, which is nothing but the solution for W explicitly in terms of x2 and x3 and implicitly in terms of x1 through gamma 11 bar and the kappa bars, right? Instead, here you have to still solve for Wi, but instead of solving for it in an analytical closed form solution kind of an approach, we would have to resort to numerically discretizing it, and this discretization, as I said, is basically a cross-sectional discretization, and the cross-section is a plane, it's a 2D surface, and therefore you have to involve 2D finite elements in this exercise. The 3D formulation and rigorous dimensional reduction to 1D implies that we have to formulate first of all the 3D strain energy density, which is already there, which is quadratic in the gammas, because we are still considering a materially linear problem, which is valid for most engineering materials that we typically use in aerospace applications. So basically it is quadratic in the gammas. D is a set of constants, but the D for the composite, as you know, is much more complicated and in general could be fully populated, and that basically brings about a difference, and of course it could have a layered configuration because of the plies in the laminate having different directions or hybrid composites, what have you, and therefore D not only will be fully populated but could also vary along the thickness direction. So these are the additional complications that you bring in to the picture. Now we define the functional, which we basically want to make stationary, which is the strain energy per unit length of the beam, which is using the same symbol as before, U1D. Basically it is having an SI unit of joules per meter along the length of the beam. Now that is in turn an integral over the cross section, and we also saw in one of the earlier classes the need for having a square root of G, because we are considering initially curved geometry over here, and therefore the volume element would have contributed this root G, though your U would be a volume integral with respect to dx1, dx2, dx3 and root G, then you would have the U3D, but because of the fact that root G depends on x2 and x3, this has to be brought into the integral over the cross section itself because of the dependence on x2 and x3, which are cross-sectional coordinates. And that's why you had a new definition, which the notation which we used for the previous simple example we continue to use in this case as well. Whereas a single arrow bracket would mean just an integral over the cross-sectional area, a double arrow integral, double arrow notation would basically mean integral of that quantity multiplied by root G over the cross-sectional area. Next, because it's an asymptotic method, we identify the small parameters. Just as in the previous case, we identify epsilon hat to be small compared to 1 and a by L squared small compared to 1, as well as a by R squared small compared to 1. This is equivalent to saying that L and R are of the same order of magnitude. They can be numerically different, of course. The order of magnitude is what matters over here. So in other words, we are saying L and R are not different orders of magnitude. If they are, then you can appropriately use that kind of a method to go for the solution. But even in a case where you do not have, for example, any initial curvature, it's a prismatic beam where R tends to infinity, so L is obviously not of the order of infinity, but still you can make a special case out of the method that we develop here to drop off the terms associated with the curvature, and then you would end up with a situation, that situation as well. The problem comes only when R becomes smaller, so that basically it becomes very small initial radius of curvature. In that situation, instead of both saying a by R, a by L whole squared, a by R whole squared, you will have to have a different notation over here instead of the 2. So that basically has to take care of the new value of R that you basically have over there. So typically a higher power. So here, of course, R inverse, because we are there in the previous example, we had only one initial curvature, which was in the plane of the board. We saw that it had almost like a circular beam that we are basically dealing with. So its initial radius of curvature was R everywhere along the length. here instead we are dealing with a more general case where we don't have K3 alone, but we also have K1 and K2, and therefore we have to, when we're talking about the small parameters, we're talking about the maximum of those. Just as in the case of the strains, we talk about the maximum of all of these 6 measured numbers of the strain everywhere throughout the beam domain, right? And R is defined in terms of that as the maximum of magnitude of all the K's everywhere along the length, because in general they can vary along the length, and you take the reciprocal of that, that is what is R, and we are saying that the cross-sectional dimension small compared to that R in a square sense. Now solve for Wi using the variation asymptotic method means that you will arrive at various levels of approximation. So the approach is very similar to what we had there, just that we'll have to discretize it in a different way in order to approach that solution over here. Now we have to substitute for Wi and integrate that U3D using this expression to get U1D, which is what we have to minimize, which means that at each level of terms that we are including and perturbations that we are making to the already obtained solutions to the warping, we would end up with series of asymptotically correct values of the energy per unit length of the beam. So as I said, this is a numerical approach, so we need to discretize the warping. So how do we go about it? We know that in the analytical solution, what happened was basically, you saw that the warping solution was obtained explicitly in terms of x2 and x3 and implicitly in terms of x1. So we can take advantage of that fact. That is always going to happen because of the fact that the length of the beam is large compared to the cross-sectional dimension. In other words, x1 is of an order of magnitude which is smaller compared to the order of magnitude of x2 and x3. Okay? So which basically means that the energy distribution completely determines the elastic body's behavior. So we take advantage of that fact that the energy distribution will basically determine how the beam is going to deform, what will be the stresses at various material point locations because of that. And that means that to derive the 1D beam theory, which is what we're going to do, we have to reproduce the 3D energy in terms of the 1D quantities. And when we're talking about deriving the 1D beam theory here, we are primarily targeting the cross-sectional analysis, which is basically the constitutive law, whereas in the second part of today's lectures, we basically will deal with the situation where we want to derive the equilibrium equations as well. But they both come from the same core, which is basically the minimization of a particular functional which is associated with the energy of the beam, various kinds of energy. It's just a fact that as far as the cross-section is concerned, as far as the constitutive law is concerned, it's only the strain energy which contributes to it. Whereas when we go to derive the overall 1D beam theory, including the equilibrium equations, we'll see that other kinds of energy and the work done, etc., will impact the equations as well. So reproducing, how do we go about reproducing this 3D energy in terms of 1D quantities? We already introduced those 1D quantities, and it's a fact that whether we are applying the VAM and getting an asymptotically correct solution or any other kind of approach that we take to go to a beam theory, whatever you get is actually an approximation. That's something you have to keep in mind. Okay, for all the rigor, mathematical rigor, the physical rigor in terms of the starting point, etc., a 3D body is a 3D body in reality. Okay, it has to, for true modeling, it has to be modeled as a 3D body. Just that we are taking advantage of the cross-sectional dimension being small compared to the length and therefore reducing it to 1D, which means that exact dimensional reduction is impossible. It's just that what is the best that we can do? What we can do is asymptotically approach the exact solution, and that's basically what we are doing using the VAM. So VAM helps find the 1D energy which approximates that 3D energy as closely as desired, and this is a linguistic term as closely, but it has the mathematical significance here in terms of the asymptotics in terms of the identified small parameters and the relationships between them. So let the order of L be the same as order of R, which is same as saying that A by L squared is negligible or A by R squared is negligible, which we already stated in the previous slide, for convenience. And as it is sufficient to develop what we are going to do now, which is a generalized Timoshenko model. Okay, so you know that the classical Timoshenko model, which Timoshenko himself derived and therefore named after him, basically accounts for transverse shear deformations in addition to what is already taken care of in the Euler-Bernoulli beam theory, and therefore letting the normals to cross sections no longer remain normal. So in other words, the normals can rotate separately from the cross section, so that additional rotation involved is basically constituting the transverse shear, which we saw can be included in two different ways, one as either as a part of warping and the other basically as a separate 1D variable, right? Now, what we are going to do is to basically derive that so-called generalized Timoshenko model, not the classical Timoshenko model, because the classical Timoshenko model is asymptotically incorrect, as I have stated in some of the previous classes as well, which basically means that we will first derive an asymptotically correct solution and then try to force that solution to look like a Timoshenko beam by basically minimizing the error between the two. And that is what would basically boil down to the so-called GTM or generalized Timoshenko model. And this we will do for a beam made of composite materials and very complex geometries. Could be an airfoil cross-section with different kinds of composite materials involved in it, some sandwich constructions, whatever. And also in terms of along the length, all kinds of complications due to the curvatures in the three different directions. Only necessary to expand all unknown functions in asymptotic series of A, because if we take order of L and order of R as the same, in terms of the geometry we now have only one small parameter, which is either A by L squared or A by R squared equivalently, right? And also we have said that that is in turn equivalent to epsilon hat, so therefore it is enough to retain just one particular quantity A as a small parameter, and everything is basically asymptotic with respect to that. Or you can think of an A bar, which is a non-dimensionalized version of A, which is either divided by L or divided by R equivalently. Now the complex cross-sectional geometry and non-homogeneous anisotropic material that we are going to deal with for the general composite case means that the numerical approach to find stationary value of functional is indispensable. You cannot go for analytical solutions except for some simple geometries like a rectangular strip or cross sections which can be construed as basically made out of a number of such strips like an I section or a Z section, etc. In all other more generic situations like the airfoil cross section that we talked about, for example, we need this numerical approach. So what we do is, we know that the unknown quantity is the warping field, that is W1, W2, W3, and this, recollect, is along the small bi direction, though when expressed in terms of the position vector, it would involve the big bi's or big ti's because of the pullback that we are basically doing there, right? So you have W is equal to W1, W2, W3, a column vector, and that W we are now discretizing just like we do in any finite element implementation, by introducing shape functions for the x2 and x3 directions and basically the amplitudes. The amplitudes would now still be functions of x1 because we are dealing with only one particular cross section at a time. In other words, your x1 is fixed to some value x1 star. So in that sense, this amplitude is actually a constant for a given cross section that we are basically analyzing. But we have to remember that when we go into the 1D analysis of the problem, and therefore we are basically explicitly writing the fact that it is a function of x1. This really doesn't matter as far as how we employ this in the solution of the cross-sectional problem itself, but just to make sure that that is kept in mind when you do the 1D analysis, right? And of course, when you have, for example, terms like W prime involved in some of the terms, the gamma 1 I terms, in such situations the V prime would come into picture as well. Now what is this S of x2 comma x3? It is basically a matrix consisting of 3 by n, 3 rows and basically n columns that you have there. A matrix of finite element shape functions, just like you would do in any other 2D finite element discretization, depending upon the choice of the elements that you have made. Right. And of course the degrees of freedom at each of the nodes. Now V of x1 again is an unknown. but this time it is basically an n by 1 matrix of nodal W amplitudes over the cross section, whereas your shape functions are already assumed, because that's what you do in a finite element analysis. You assume certain shape functions depending upon the elements that you choose, and basically the nodal degrees of freedom that you have. Based on that, you have chosen the shape functions explicitly as functions of x2 and x3, whereas V is still unknown. It's the nodal W amplitudes of the warping over the cross section. Now, so therefore W is equal to S times V, okay, and this S times V, so in terms of the unknown quantity, now it's basically V, because S are the assumed shape functions, so V become the unknowns instead of W. So that's basically what we are going to try and determine now. Of course, it is the actual values at different points along the cross section, which are the nodes of the elements involved. Now we substitute that into the expression we have for the 3D strain. And remember that the 3D strain was broken up into 4 parts, 3 depending on the warping, 1 depending only on the strains epsilon bar, right? Still we deal with only the 4 degrees of freedom, which the variation asymptotic method itself basically brought about. We are not bringing in those 2 additional degrees of freedom, which is basically the transverse shear strain measures. That is something we will force upon this method later, okay? So we know that it has only 4 degrees of freedom, and those 4 degrees of freedom are contained in this, and those warpings in turn, when we solve for it by minimizing the strain energy per unit length, we would see would in turn become functions of that epsilon bar, and basically the entire strain energy is a function of that epsilon bar, which is what leads to the 1D constitutive law. So let's go about recollecting what each of these quantities were, these matrices that you have here. Some of them are differential operators like these, and a couple of them are basically just matrices which multiply whatever is existing over here, namely these 2 matrices multiplying epsilon bar and W prime respectively. Now we substitute this W is equal to SV in this, and then we substitute this gamma expression into the expression we have for the energy per unit length, unit volume of the material, which is basically nothing but equivalently the constitutive law of the material which is being used. And as I said, in general, your D can be functions of the thickness coordinate, for example, or for that matter even the x2 coordinate. For example, you can have an airfoil in which the leading edge is made out of a different material, the trailing edge is made out of different material, skin is made out of different material. So you can have the material varying in both the x2 and x3 directions, apart from the x1 direction, of course. So that D is in general a function of x1, x2, x3. Then you have your gammas, which are functions again of x1, x2, x3, because they are the 3D strains. Now we are substituting that using this particular relationship, so basically putting it on both the sides here with a transpose, and then you basically multiply each term with term. So obviously you're going to get, there are 4 terms on either side. So basically if you're thinking of it in a matrix kind of a scenario, a submatrix kind of a scenario, you're basically going to have 4 kind of quantities which are going to multiply with a similar kind of quantity, and basically it's like a 4 by 4 matrix which has 16 elements, and then you basically have 4 diagonal elements. So the remaining 12 would divide into both sides of 6 and 6, which are basically coupling between one kind with any of the other kinds that you have here. So each of these has some kind of an interesting meaning to it if you try to interpret them. We'll see if we can do some of those. So now what we do is we substitute this U3D in the expression for U1D, which is nothing but the integral over the cross section after multiplying by square root of G, and that's why you see these double brackets over here, double angular brackets. Now introduce matrices containing information on cross-sectional geometry and material properties. If you leave them as it is, it becomes quite messy. So we introduce certain new notations for new variables, which are basically in some sense products and integrals over the cross section of various quantities, using these matrices of course, and the matrix D, which contains all of the material information. So that is basically what we will do, containing information on the cross-sectional geometry and the material properties. The way the cross-sectional geometry enters, of course, is through this, and of course over the integral that you have over the cross-sectional area. So first, we'll add term by term. The first term that you will have in U1D is basically by multiplying the first terms in both of these sides, which is basically gamma A SV and gamma A SV on both these sides. And that's when you multiply, you see that the unknown quantity basically is V. So it's basically V transpose EV, and that half would still remain because there's only one such product, whereas the cross products will be two. For example, if you multiply this with this, you can have one term like this, and similarly another term like this, which would have the same quantities, and therefore the two will cancel with the half. But here it doesn't, because they are both of the same quantity. Now what we are doing is, basically the rest of the quantities we are clubbing into a single variable, which we shall call as E. Okay? And that E is of course defined in terms of this matrix gamma A, which is a differential operator, acting upon the shape functions. Remember that the shape functions upon the choice of the specific element and the nodal degrees of freedom are functions, explicit functions of x2 and x3. So you're basically taking derivatives of that with respect to x2, x3 over here, and that's basically what you're doing here. And then of course multiplying by the material matrix and itself, and integrating over the cross section after multiplying by root G. So in other words, it also contains information about the initial twists and curvature as well, apart from the cross-sectional material distribution, material properties, and the geometry. Next we go to the second, of course the order of the matrices is important. So E, for example, is an n by n. That is quite easy to see either from this by knowing the orders of each of these, but even more easier if you look at this, because this has to be a scalar quantity, and you know V is a column matrix of order n, so you're basically multiplying V on both sides to get a scalar quantity, so you know that E has to be an n by n matrix. Okay. Next, the second diagonal term that we have, and therefore the second contribution to the energy is once again basically the second term over here and the second term over here. This is a very important contribution because it's direct contribution from the 1D strains, the 1D classical strain measures, and that is basically contained in a matrix. Except for this particular element, all other matrices we will call as D without this floral notation. This is a floral D containing only material information, whereas all of these Ds, regular Ds, contain material and geometric information, geometry of the cross section and the geometry of the initial twist and curvature as well, right? So basically you have in this just gamma epsilon transpose D multiplied by gamma epsilon, and that basically contributes to this term, and that is a 4 by 4 matrix because we have just the 4 classical strains associated with it: gamma 1 bar, kappa 1 bar, kappa 2 bar, and kappa 3 bar. And so that is basically what you see over here as well. Contributes another scalar term to the energy per unit length. Similarly, the third term, which involves the contributions of the initial curvature, primarily, though of course initial curvature is contained into these as well. This is a direct primary contribution from the initial curvature, DRR term, because it basically comes from this gamma R, and if there were no initial twists and curvature, you would see that K1 and K tilde would go to 0, this entire matrix would be equal to 0, root G of course would be 1, and therefore your gamma R would be basically zeros, and therefore you would not have anything at all over here. So if there was, if you had a prismatic beam, this would go to 0. So this is an n by n matrix that you have here, and of course the corresponding term is again V transpose V, very similar to this. Then you have the fourth diagonal term basically coming from these two, which we call as DLL, which is again an n by n matrix because associated with V primes in both directions. Typically the contribution of this will be very, very small because this, remember, is a representative of the warping without the shape function, and basically that derivative with respect to x1, where x1 is a very large quantity, the length is large compared to the cross-sectional dimension, so it basically has a small contribution in general, but it can play a crucial role in some situations, as we shall see shortly. So V prime transpose DLL times V prime. So remember that we have not yet applied the variational asymptotic method. In order to apply the variational asymptotic method, we need a functional, we need small parameters. We have identified the small parameters. What we are doing now is to set up that functional. That's basically what we are doing. And then we will apply the variational asymptotic method by dropping off higher order terms in this.
So again, is number of nodes, right, sir?
Yes, that's correct. So basic, so next, it's actually the number of degrees of freedom. So it includes the see, you are putting W as S into V, right? So basically it's the shape functions into the amplitudes at each one of those nodes.
Yeah.
Right. So it has to be equal to the number of nodes that you have.
Sir, n is
So
3 times the number of nodes.
Yeah. 3D freedom it is.
At each node 3 was.
oh yeah. So you
N
have
is
3.
3.
No, but you have S into V. S is a 3 by n, right?
Yes.
Yeah.
So your this is n by 1. So that 3 is already taken care of in the 3 rows of S. So next we go to the coupling terms. So we take the first term on the left hand side and the second term on the right hand side. So you have a V transpose coming from that and basically an epsilon bar coming from that. So you have a dA epsilon associated with that, whose expression you see over here. So basically you see that in most cases you would have the operator operating upon the shape function, but that's only if the warping terms were involved with it. In the simple situation where only epsilon bar is there, that shape function will not come into picture at all in the definition of the corresponding D. So the first term is first coupling term is dA epsilon. The next is dAr, that multiplies V, of course V on both sides, and then you have something associated with V and V prime, which we call as DAL. Now again, the naming would become a little clear to you. If it were named according to the same convention, this for example would have been DAA, because it's associated with a gamma A kind of contribution, basically derivatives with respect to the cross-sectional coordinates, and then you have, which is associated purely with epsilon as epsilon basically, and then with the curvatures, because this is where the curvature comes into picture, and that's included in that, and all primes are basically included in this, though of course you see only numerical constants over here. You can see that basically it's associated with the primes in the warping. That's basically because of the W prime that you have here, and that we call as L. So basically there are 4 types of subscripts here: A, epsilon, R and L. A associated with the cross-sectional dimension, epsilon associated with the classical strain measures that we have already extracted, R associated with the initial curvatures, and L associated with variations of the warping with respect to the x1 direction. Next, of course, the other off-diagonal terms, fairly obvious, dr epsilon. Then you have basically d L epsilon and drl, and finally, okay, I guess I'll finish. Right. Okay. So that's basically what you have. Then we go on to use the expression that we have for the functional to establish the 0th order approximation, which means that we have to retain only the leading order terms in the functional that we defined as the last line of the previous slide, and then basically minimize that with respect to the V, and then we basically obtain the governing equations for that. So now use the shape functions S to express the kernel matrix Xi, which is basically this, which is again something which should not contribute to the warping because those are things that have already been contributed for by the rigid body degrees of freedom, which are contained within your gamma 11 bar and the kappa bars, right? So now that Xi, we will write it as S times Xi. So once again, remember that your S is a 3 by n matrix, and your Xi, capital Xi, would be n by 4 matrix, which would contain the nodal values x2 and x3 of all of those nodes, of the n nodes that you have, and that's why you have a n by 4 matrix over there. Of course, this submatrix within Xi is just an identity which would keep repeating. So we have used the shape functions yes to express the kernel matrix also in terms of the kernel matrix's nodal values in that matrix with the capital Xi, right? Now you go back and look at your notes. You remember that the way we introduce the constraints, we said it's not sacrosanct. It's one way of introducing it, and that gave an interesting physical meaning to the variables, and therefore we retained that all the variables, especially the U's and the rotation variables, and that's why we chose that particular thing. And the way we introduced that was basically means that gamma A times xi is equal to 0, where xi of course is this matrix, and gamma A is the matrix containing a row of zeros and then derivatives with respect to x2 and x3 that you saw in the previous slide. So now we substitute for xi using the numerical discretization we have s times xi over here. So gamma A times s times xi becomes equal to 0. Now from the previous slide, also recollect the symbol E that we introduced for this stiffness matrix and intermediate kind of a stiffness matrix that we have. So basically is this quantity, right? Now if you multiply this E with this xi, it is quite obvious that it is equal to 0, because if you put xi here, remember that xi is not a function of the cross-sectional coordinates because it already has the numerical values of x2 and x3 of all of those quantities. It can be taken basically inside here, so then it will s will multiply xi, and s times xi is what you have there, along with gamma A, which is basically equal to 0 because of the particular choice of constraints that we have. So basically this term along with xi would go to 0, which means E times xi would be equal to 0. Now you can transpose this. Remember that E is a symmetric matrix, so if you transpose this, it becomes xi transpose into E transpose equal to 0. E transpose is equal to E, and therefore xi transpose times E is equal to 0. Now we substitute this discretized form of the kernel matrix into the constraints itself. The constraints, remember, were such that the warping should be orthogonal to the solutions which is indicated by the kernel matrix, and therefore W transpose times I integrated over the cross section equal to 0. And here note that it's not a double angular bracket, so no root g is involved here. It's quite easy to see what it means from these three is that average of W1, average of W2, and average of W3 equal to 0. And here W2 times x3 with a negative sign, and added to that W3 times x2 integrated over the cross section equal to 0. So that is a compact way of putting all the four constraints, rigid body constraints, into a single thing. In fact, it is from this that we derive those scalar representations of the constraint. Is a matrix equation representing the set. Now we go and substitute for both W and xi in the numerically discretized form. Your W is nothing but S into V, so therefore W transpose becomes V transpose into S transpose. Then your xi, which we got over here as S into xi. So this is basically what we have as equal to 0. This takes care of all the constraints in a numerical fashion. Now if you look at this, your V is not, this integral is over the cross-sectional coordinates x2 and x3. V is not a function of x2 and x3 because the actual values of x2 and x3 are already substituted into it. It's just a numerical thing, which of course has to be determined, the unknown quantities, the amplitudes of the warping. So basically that comes out. And this xi, which is basically the numerical values of x2 and x3, is also a constant that which is with respect to x2 and x3, and therefore it also comes out. And you just have an integral of S transpose S, for which we will give a new name, new notation. We'll call that as H. So H is defined as the area integral of the shape function transpose multiplied by the shape function itself. Right? This implies that the constraints in the discretized form can be written in a much simpler fashion as just V transpose times the integral of this, which is H, times capital Xi equal to 0. So this is what we will use as the constraints hereafter. Now you note that the Xi transpose H Xi is nothing but equal to the integral of Xi transpose times Xi, and if you actually work it out, it turns out to be nothing but this matrix, which involves the first moments of inertia as well as the second moments of inertia as some of its non-zero terms. Now to use the variational asymptotic method, we already have the function, we already have the small parameters. All that we do is to get the zeroth order approximation, first find the functional called u1d naught, which contains only the leading terms. So for the zeroth order approximation of the strain energy, the leading terms have to be of the order of the material stiffness quantity, which we can call as mu or E, not to confuse with this E. This E is different, this symbol is different. I would rather use a mu for this to be distinct from the rest, though of course mu is also used for something else later. Anyway, just remember that these E's are different. This is just the order of magnitude of the any quantity within that flowery D, which is the material stiffness matrix, right? So that, and of course there's an integration over the area, and therefore this is A. For a class R beam, it would just become small a squared. And then you have, because it's quadratic in the strains and we are taking only the leading order terms, the leading order terms in the strains will be of the order of epsilon hat, and because it's quadratic in that, it is of the order of epsilon squared. So this is the order of magnitude of the terms we have to retain in U1D.
So, what is not clear why this warping W transpose multiplied with psi, it is excluded that root G term.
Yeah.
Yeah, what is excluded the root G term?
See, basically the root G, what is the source of that? It is, the source of that is a volume integral,
Yeah.
right? The constraints do not come from a volume integral, they come from a pure area integral.
That means, particular for this case, we are we can exclude the root G. If it is
No. See, the root G comes into picture only if an area integral is inbuilt into a volume integral. So for example, your total energy of the beam is equal to volume integral of the 3D strain energy density, right? That volume integral can be broken up into two parts, integral over the cross section and integral over the length, right? Now the integral over the cross section is an inner integral, right? So that inner integral will contain that root G because it was part of that volume integral, but it's also root G contains x2 and x3, 1 minus x3, k2, etc. right? So you have the x2 and x3 dependence, so you cannot take it out of the cross-sectional integral. So that's why it comes into the cross-sectional integral. On the other hand, the way we introduce the warping constraints is when we are dealing with a cross-sectional problem. We are not even bothered about the length of the beam. It's a specific reference cross-section that we are dealing with. So the root G doesn't come into picture at all. Okay. See, basically what you have is x1, x2, x3 are Cartesian coordinates, but x1 alone is a curvilinear coordinate. Your x2 and x3 are still linear coordinates. Okay, and that's why you see that anything dealing directly or purely with the cross section does not have that root G. Whereas if that is coming from a volume integral and partly the inner integral is being calculated, then you have that root G term coming into picture as well. So this is the order of the terms that we have to retain. Anything which is higher order than this, we will drop off. So your EU1D naught, then you would see out of the many terms that we had there, the four diagonal terms and basically the off diagonal terms that we had there in that 4 by 4, which is 16 minus 4 is 12 divided by 2, 6. So 6 off diagonal terms. Out of the diagonal terms, basically these two are the only ones which come. The other two get dropped off as higher order terms. It's quite easy to see because one is associated with the curvatures, and because A by R is a small parameter, those terms drop off. And the other is associated with V primes, and because A by L is a small parameter, those terms drop off as well. And of course, amongst the interaction terms, it's the interaction between these two which remains. All the other interaction terms are higher order interactions and they drop off as well. And this, if you look at, of course this term contains only constants. When you take the variation of this will contribute as 0. So what is of interest in terms of a mathematical sense is only these two terms in determining a solution, the 0th order solution for V, right? So if you look at this, one has a bilinear form. If you remember the forms that we introduced, the linear form, bilinear form, etc. So it's a bilinear form, and the other is a linear form. This epsilon bars are assumed to be known right now because we have fixed x1. Epsilon bars are all functions only of x1 and of course time, but basically at a given cross section and a given instant of time they are fixed. So basically the only unknown is their v, and that's a linear form. So a combination of a bilinear form and a linear form is what is a quadratic form, and one of the first examples that we applied the variation asymptotic method to was to determine the stationary point of a quadratic functional, a general quadratic functional. And we basically will utilize those solutions in solving for this as well. Though of course it can be done separately also. Because we have already done that, we take advantage of that. Now the problem transforms into a minimization of U1 D naught as far as the 0th order approximation is concerned, subject to, of course, the constraints which are also now in a discretized form, which is basically V transpose H xi equal to 0. Now we introduce Lagrange multipliers, as is done in all calculus of variations problems. When you want to introduce the constraints, one way of doing it is by introducing Lagrange multipliers. You multiply those. The Lagrange multipliers are also unknown quantities, and then let's say we call them as minus lambda 1, minus lambda 2, all the way to minus lambda 4. So matrix of Lagrange multipliers. Again, we have a column matrix over there. Now we basically add a term which is minus V transpose H xi lambda to the original functional that you have over here, and then you basically minimize that instead of minimizing U1 D naught alone. It's a new functional that you define in order to take care of the constraints. And that results in the Euler-Lagrange equation. It's quite easy to see because the quadratic or the bilinear term will basically contribute a factor 2 that will cancel with this half, and so you will end up with only an EV, whereas here this will drop off and you will have only this term, which is basically dA epsilon bar, and coming from the constraint, basically again it's linear in the V's, so this drops off and only you have H xi times lambda, because the Lagrange multiplier is also there over there, right? And of course, because the reason why we introduce the negative sign is so that we can take it to the right hand side and make it positive, because lambda is an unknown, we can absorb the negative sign into it just for convenience. So now we have to solve for those Lagrange multipliers. So in the previous slide we wrote the Euler-Lagrange equation, which was the governing equation for the V's, to be determine the V's in terms of epsilon bar. Because it is discretized, it's not appearing in the usual form that you see as a differential equation. Instead, it's an algebraic equation that has to be solved. But there are two unknowns here. One is V and lambda, and you have to solve for both of them. Epsilon bars are assumed to be known, though of course they are the 1D strings. Now, to solve for them, we do some matrix manipulation over here. We multiply both sides of this equation by the xi transpose. Xi, remember, is the capital Xi, which is the discretized form of the kernel matrix. So that's what we do. So xi transpose EV plus, now you can see the reason why we do that. In the previous slide we showed that xi transpose times E is equal to 0 because of the definition of E in terms of gamma A times S, and gamma A times S times xi is nothing but gamma A W, which is nothing but the form of the constraint, so this term will drop off. Of course you have xi transpose multiplying the other two terms in the equation as well. So E times xi is equal to 0, and therefore xi transpose times E is equal to 0. We showed that in the previous slide already, and we retain only the other two terms, that is basically these two. Now it is quite easy to see that the V has been eliminated out of this equation, out of the two unknowns, two sets of unknowns rather, of V and lambda. We have removed V by a matrix manipulation and employing the constraints, and then we can solve for this lambda by taking this to the other side, inverse. So basically Lagrange multiplier is calculated as xi transpose H xi inverse times xi transpose times dA epsilon times epsilon bar. Now we substitute this lambda into the Euler-Lagrange equation, because now lambda is known in terms of the other known quantities or assumed to be known quantities, and therefore the only unknown which will be left in the Euler-Lagrange equation would be V. That can be solved for as well. So your EV now becomes this. Your lambda has been substituted over here using this expression that you see, and then you see both the terms are proportional to epsilon bar. So you see that basically your V solution is going to be proportional to epsilon bar. This would be a fairly easy thing to solve if you are able to invert E. But remember that though the right hand side has already taken the constraints into account, the left hand side in the definition of E, the way we define, has not yet taken the constraints into account. Or in other words, out of the n degrees of freedom that you have, it is such that if you take the eigenvalues of E, for example, you will get 4 zero eigenvalues. So in other words, there are 4 singularities associated with E, and therefore you cannot invert E and determine the V. So you need a special approach to this, and this is a standard approach in matrix algebra to determine the solution in the situation where the coefficient matrix contains 0 eigenvalues, and that's basically what we will do here as well. But before that, let's put these things together. Remove dA epsilon bar, which is the common factor in both these terms. Put an identity matrix instead over here. And now you see that the constraints are already applied, which means that the right hand side is orthogonal to the null space of E. Okay, so that's basically what I was telling. The constraints are already incorporated on the right hand side, but whereas the way we defined E and the way we introduced V, at that point of time we had not introduced the constraints, and so therefore the singularities remain on the left hand side. So right hand side is orthogonal to the null space of E, and which in turn implies that the unique solution for V exists linearly independent of the null space. Of course, the V should have a solution. It's basically the amplitudes of the warping. It has a unique solution, and that exists linearly independent of the null space. Now we will see how to take care of the 0 eigenvalues of that. From the previous slide, we're just repeating this, and now explicitly stating what are the orders of each of these matrices. E is n by n, V is n by 1. This coefficient that you have is n by n, including this identity matrix as well, and then an n by 4 intermediate stiffness matrix dA epsilon, and of course your classical measures in a column matrix of size 4. Now the solution for V is unique, but as I said, E is singular, so we have to eliminate the 4 singularities of E. So that can be done in any arbitrary way to get an intermediate solution, which is not the solution that we are seeking for V, but we can use that intermediate solution to get the actual unique solution for V. So that's basically what we will do. Some arbitrary way we will constrain the nodes or the nodal values in such a way that any 4 convenient constraints can make the problem determinate. So what for example VAPS does is to constrain any 4 of those n degrees of freedom that we have for the V's. Okay, so once it does, it gets an intermediate special solution V star. Note that this is not the solution that we are seeking. There is only one unique solution for V, and this is not what we are seeking. It is just a mathematical intermediate quantity which we shall use, along with the fact that the right hand side is already orthogonal to the null space of E. Okay, that fact we will use to add to this solution to get the solution that we are seeking. So in other words, your V, the actual complete unique solution that we'll have, will be this special solution, which is found by just constraining arbitrarily any 4 of those degrees of freedom. Remember that they are all independent degrees of freedom. So constraining 4 of those n degrees of freedom, and then basically solving for it. Once you're solving for it, then you basically say that you are adding that nodal values of the kernel matrix multiplied by some lambda should be basically add to give to your V. So in other words, the additional term should be proportional to that kernel, the nodal values of the kernel matrix. Now we don't know, so we have introduced a new unknown, which is basically lambda, which has to be determined. V star is already determined. Once we determine lambda, then V can be determined as well. So in order to determine lambda, once again we have to go and take advantage of the constraints. So we have to find it, and from the size of this matrix we know this is n by 1, this is n by 1, so, and this is basically n by 4, so this has to be 4 by 1, right? So your lambda has to be a 4 by 1 matrix, and to determine that, what we will do is we will transpose the constraint equation, V transpose H xi is equal to 0. That is the constraint equation in the discretized form which we derived earlier in the class today. And so when we transpose that, it will become xi transpose H transpose, because H is symmetric, because remember H is defined as the integral over the cross section of S transpose times S. So that is a symmetric matrix. So H times transpose of V transpose is V. So that is basically equal to 0. Now this should hold for the actual V, the unique solution that we are looking for. That V is nothing but the specialized V that we had, V star, plus xi times lambda. So we can substitute that here and then solve for lambda using this constraint equation. So that's basically what we'll do. So V is written as V star plus xi times lambda over here, and then you retain the lambda term on the left hand side, take the other term to the right hand side, and so using this and inverting this, we can determine lambda in terms of V star. So lambda is basically minus the inverse of xi transpose h xi times xi transpose h times V star. So then once we have lambda there, you can substitute back lambda here to get the actual solution, which is V, which is proportional to your V star, which is that specialized solution that you got, and basically the quantity that is multiplying the matrix that is multiplying it is basically the n by n matrix as shown. And so you can see that this in turn, because of the structure of this governing equation over here, V is proportional to epsilon bar. Okay, so once you solve for this, you would see that using this procedure that we described, eventually you will get a solution for that, and you would see that your n by 1 matrix of the amplitudes of V would basically be proportional to your epsilon bars, which is of course expected because those were the actual degrees of freedom of the beam, the 4 degrees of freedom, and anything that comes out, the warping, etc., or the perturbations to the warping, which we shall return in the next level, etc., should all be eventually functions of those 4 degrees of freedom, namely your extensional strain, the twist per unit length, elastic twist per unit length, and the 2 bending curvatures. And the warping is linear in epsilon bar, as is expected at this level. So now we can use that solution to substitute into the strains and the 3D strains back into the energy to get an expression for the 0th order energy. And suppose we call what we called as E earlier, suppose we call that material moduli as order of magnitude mu, they are both the same. Substitute that expression we got for V as V naught hat times epsilon bar, where in the actual numerical problem we would have got the actual numerical values of this n by 1 matrix, the n by 4 rather, to get multiply the 4 by 1 and get your n by 1, right? So this would be n by 4. So you would have got the numerical values for that. You would, when you substitute that into the expression that we have for u1d naught, which is basically this, and retain only the terms which are the leading order terms in that particular thing, which is up to order mu times epsilon hat squared. And you can see this, there is a parallel between the general case of the quadratic functional that we took for the variational asymptotic method minimization as well. You can see the parallel in that as well, that your u1d naught will basically boil down to this expression. And then you see now that it is quadratic in the epsilon bars as is expected. Your warping is linear in the epsilon bar, the strain is linear in epsilon bar, and because the strain energy is quadratic in epsilon bar, therefore you see epsilon bar on both the sides, and this matrix that between the square brackets over here becomes your so-called stiffness matrix, the 1D stiffness matrix at this 0th order approximation, and that in general turns out to be a fully populated matrix that you have here, involving all kinds of coupling between extension, twist, bending, twist, extension, bending, between the 2 directions of bending, etc., all contained within this S bar, but of course obtained numerically using the finite elements. Asymptotically correct energy without the correction for initial curvature and twist, because remember that in all the terms that we basically had, we didn't have the DRR term or DAR or DA, DR epsilon or DR L, etc. So basically the corrections due to the initial twist and curvature are not contained within this. So that is quite obvious because A by R was treated as a small parameter, and here we are only interested in energy of the leading order terms, mu into epsilon hat square, and then you can see that the corrections for initial curvature and twist are not there. In case you need to get that, you have to go to perturb the warping solution that you had, and basically then you have to solve for that particular warping, which is a higher order perturbation compared to what was already found as the solution, namely this, and then you basically have to substitute that into the energy and retain not only mu into epsilon hat squared, but also mu into epsilon hat squared times A by R. So that is the A by R corrections that you would have, and then you would see the effect of initial curvature and twist as well. That is one way of approaching the problem. Now this simple model itself yields acceptable results for as it is, even without the initial curvature and twist corrections. This simple model itself has been demonstrated in a lot of examples with comparison to both 3D finite element analysis as well as comparison to a lot of experimental results with composite beams in general. So this simple model yields acceptable results, but for a specific category of problems. Those are long wavelength, static and dynamic behavior of isotropic and anisotropic beams. So in other words, what we are basically saying that is that A by L and A by R are indeed small parameters, very small. In such situations, you will see that this alone can give very accurate results. But if you want to tackle situations where you're talking about a little higher frequency dynamic problems, basically short wavelength problems that we're talking about, in such situations, of course, we have to go for the next higher order corrections. This is, remember, the most basic solution, or the so-called zeroth orders energy that we're talking about here. Now this classical 4x4 stiffness matrix of S bar that you see here can be improved for initial twist and curvature, as I already said, by taking perturbations with respect to A by R. In other words, you add to the warping solution higher order term, which is not only epsilon hat times A, but also epsilon hat times A times A by R, which is the higher order correction, and then retain up to that level in the energy and minimize that. The goal is a more general approach. On the other hand, what we will do is not that. We are not seeking only A by R corrections, because our interest is not only in the effect of initial twist and curvature. We also want to capture transverse shear effects, because remember that at the beginning I told you we are developing a generalized Timoshenko model, and Timoshenko model, the primary contribution is in terms of the transverse shear deformation, but of course for an initially curved and twisted beam, the contributions of curvature should be there as well. But both of these can actually be achieved with a single stroke, because of the fact that we have assumed L and R to be of the same order of magnitude, or in other words A by R and A by L to be similar kind of small parameters. So the more general approach would be to regard both A by L and A by R as important, of the same order. This is what we already said. And now let's call that ratio, or the order of magnitude of that quantity, as A bar. Okay, so you know that A bar is a small parameter. Now purely A by R corrected theory would then become just a byproduct of that general approach. You just have to drop the transverse shear terms, or basically the A by L correction terms, then you would get only A by R, which is what we would have done if we wanted to only get that as an addition. That's what we would have done. But here, by including both of them and trying to get both of them, the byproduct of that would be to get just the A by R corrections alone as well, because we're going to get both of these corrections simultaneously. So that's what we will do in the asymptotically correct refined model for composite beams. I'll finish these also because I have just very few slides for this, and then we'll take a break before we start the 1D theory for beams. So what we're going to do now is very similar to what we already did. The same problem we're going to take up, but we're going to go to the next level. That's basically a refined model. It's again the same general composite beam that we handled previously. So we will use all of the results that were there. We'll perturb that and then go for the so-called refined solution. Asymptotically correct refined theory. First of all, the theory aspects of it. We perturb the unknown warping field as a series in the parameter A bar that we introduced as the last slide of the before the title slide, and there that was basically either order of magnitude of A by L or order of magnitude of A by R, right? The initial radius of curvature. So in that sense, if you think of V as being expanded in a series of A bar, which is a power series, then you'd see that already we obtained this V naught, which are the leading terms, which was the solution for the zeroth order approximation. The next term would be proportional to A bar, or would have the order of magnitude A bar rather, related to that. In other words, V1 divided by V0 would be of the order of magnitude of A bar. Similarly, A bar squared, etc., and terms, higher order terms as well. Now,
always we have to expand in terms of normalized units, so that like the dimension of
that's correct. That's correct.
V1 should be
Unless and until you have only one small parameter and you have an assumed way of doing that in a consistent fashion, which is what you would do. For example, here, everywhere you know epsilon hat corrections you're not basically taking into account, so that is already set aside. And the only two small parameters are A by L and A by R, both of which are assumed to be A bar, and therefore you can do. But as you said, strictly speaking, it's always best to do it in a non-dimensional fashion. But you see in the literature, people doing it with respect to dimensional variables as well. But as long as you do consistently, there's no issue. So we substitute into the, sorry, this is not the full expression for U1D. So these are the all the terms of U1D. So you remember we derived that earlier today. So basically, this is what is the exact expression for the 1D strain energy density, the energy per unit length of the beam, basically obtained by integrating the U3D over the cross section, right? And of course, the cross sectional integrations are all contained within these D matrices and one of the E matrix. Now, the goal is to obtain an asymptotically correct energy, which is a little smaller compared to mu epsilon hat squared, which is basically involving the A bar squared terms. Okay, so that is basically what we are trying, because that is what would bring into picture the transverse shear as well. Okay, apart from the initial curvature corrections. So it's unnecessary to find A bar squared V2, because that will contribute an even higher order of magnitude terms over here. So in other words, we don't need that. We can stop with just the first two terms. This is already determined. This is the unknown. So basically, this alone is sufficient. So in other words, we determine V1 in terms of V0 and epsilon bar. So basically, if we substitute just those first two terms into this expression and expand out, this is basically what you would get. Again, there's no point in going into details, just a substitution of a sum of two quantities instead of V everywhere in all of these terms. Now you recollect that the strain energy per unit length, that this level, that is the first order approximation, and therefore given the subscript Roman 1 over there, gets integrated over the beam length to give U, right? So you have two levels of integration. You had the three-dimensional strain energy density, energy per unit volume that was. You integrated that over the cross section, you got this, and eventually this has to be integrated over the length to give the total strain energy of the beam as a whole, right? What this means is that we integrate U1 D1 by parts to get rid of the derivatives of the warping V1 prime and ignore the terms evaluated on the boundary. Now we want to get the governing differential equation for V1. Of course, it is discretized, so it won't be a differential equation. It will be just an algebraic equation that you have to solve. So all that we have to do is determine V1. So what we see here on the other hand is there are primes as well. Of course, V0 prime, there's no problem because already we know V0. So there's a way of determining the V0 primes. So in at least in a mathematical sense, in terms of an expression. But basically the problem comes when you have the, you don't have V1 prime?
Yeah, we have.
Yeah, over here. So you see when you have the V1 primes, right? So what we would do is basically you know that what you are actually minimizing is the total energy. So then you it's basically an integral of this over the length, and there we introduce the integration by parts so that we can transfer the derivatives with respect to x1 from V1 to its coefficient. Okay, so that's basically what we will do in all the terms which are involving a V1 prime. And then, of course, the boundary terms do not matter to us because all that we are interested in is solving for the V1 in the interiors. So now the asymptotically correct refined warping. So what we saw in the previous slide was the asymptotically correct refined energy. Now we are trying to get the warping associated with that. To do that, we will introduce again two new notations. All these new notations are introduced just to make the equations look compact and try to make certain inferences from the solutions. Otherwise, there's no hard and fast rule why you should introduce all of these quantities. It just makes life simpler. So now we introduce dr and ds. dr are involving all the terms which are associated with initial curvature, and ds involves all the terms which are associated with the length correction. So basically, because of the prime quantities, that's why you see in all these an L subscript is there, whereas in all of these an R subscript is there. Now functional is to be minimized containing the leading terms in V1, because that is the unknown now. V0 has already been determined at the 0th order approximation. The new unknown is V1. So we need to retain only terms which involve V1 and which are leading order terms in V1. So that basically will lead you to a functional, an approximate functional, from which an approximate solution to V1 can be determined. So now this is what that functional is. Looks very similar to what we had in the 0th order, except that now we have some terms which are having a prime. The reason is the integration by parts that we did in the previous slide, where we transferred the derivative with respect to x1 which was on v1 to the rest of the terms, and therefore we got the prime over here. Now we solve for the first order approximation of the warping, and we would find that unlike in the previous case where apart from v0 there was only epsilon bar, and therefore v0 turned out to be linear in epsilon bar, that was the solution. Here it depends on both epsilon bar and epsilon bar prime, and therefore we would have a solution like this. So there would be a term which is dependent on linear in epsilon bar, and a term which is linear in epsilon bar prime. And epsilon bar prime is the way the one-dimensional generalized strains change along the length of the beams. Okay, of course they change along the length of the beam in general, and that's basically what basically takes into account. And once again, we are consistent with the way we use the notation. R associated with initial curvatures is associated with what is happening along the length of the beam because of the derivatives, and that's why we have one R and one S associated. The one, of course, referred to the fact that it's the first perturbation to warping. That's basically V1 that we are talking about here. So now we substitute this V1 into the U1 D1. Basically, once we get the solution, we have to substitute back into the energy, and that energy would give you the asymptotically correct refined energy, that is at the first order approximation. So what is this asymptotically correct refined energy that we have here? In order to understand that, again we will introduce four matrices. All of these are there in your textbook, so you don't need to worry about taking this down. Just follow me in what I'm talking over here. It's basically the content, the quality that is important over here. So you introduce these four matrices, and in terms of those four matrices, you can see that you have U1, D1. And it's quite obvious to see because your V1 depended on both epsilon bar and epsilon bar prime. When it depended, for example, V0 depended only on epsilon bar, then you had just one term which was quadratic in the epsilon bars. Now you have two quantities, epsilon bar and epsilon bar prime. So basically you will have a quadratic in epsilon bars, you would have a quadratic in epsilon bar primes, and then you would have the interaction term between them. But you also get a term which is having the second derivative of epsilon bar also coming into picture in the U1 D1, because remember that your energy has derivatives with respect to the x1 direction as well, and one of the terms which comes from that, because you have the warping solution depending on epsilon bar, therefore you will have epsilon bar prime, therefore its derivative with respect to x1 will have a double prime as well. And then you can see the orders of magnitude of all of these quantities. Obviously this will be the leading order term, and again these will all be higher order terms compared to this. That's why we call this the refined energy. It contains not all terms of the same order of magnitude. It contains the leading order terms and the higher order terms. But within this also, you see that all the terms that are there here were not there in the previous approximation. Only a subset of these were there in the previous approximation. If you remember the expression that we had for A over there, it only was the first two terms over here. Okay, so you didn't have all of these additional terms over here. So not only has it added other kinds of terms, that is the involvement of epsilon bar prime with epsilon bar prime itself, and epsilon bar with epsilon bar double prime, etc. But it has also changed what was already there, that is that stiffness matrix. If you remember, what we wrote there was the S bar matrix, S bar 1 1 to S bar 4 4, a 4 by 4 matrix that we wrote there. That matrix is now modified. It was only these two terms earlier, now it has additional terms as well. The strain energy expression is asymptotically correct, but not in a useful form. The reason it's not in a useful form is because of the presence of all of these primes and double primes. Okay. What it means is that if you want to directly use this strain energy, you know it is asymptotically correct. It's better than the theory that you had in the previous slide. But if you want to go ahead and use this directly, it will involve certain boundary conditions which will involve derivatives of let's say the rotation, etc. For example, if you take a cantilever beam, you typically talk about, let's say, just the displacement and rotation at one of the ends equal to 0, and then you know the force or moment at the other end, and basically you evaluate things related to that. In this case, you can have additional boundary conditions which are required because of these prime quantities, because remember, the governing differential equations will be derived by minimizing the total potential or using a Hamilton's principle, later we will see. And there, if we have these kinds of terms, or even these kinds of terms for that matter, you will have additional boundary conditions which are resulting, because you would have to transfer these derivatives on, and when you do that, you have to use integration by parts along the length, and when you do that, eventually you end up with some more boundary conditions associated with the ends, or the existing boundary conditions will have terms which are additional terms which are more difficult to deal with and not physically intuitive to you. Okay, not that it is impossible to deal with, but it's more complicated than usual. That is one of the disadvantages of this. The other, of course, is the fact that you want to compare with theories in the literature, and none of the theories will have these kinds of terms. So, of course, in the case of class T beam, you will have a kappa 1 prime. That's about the end of it. So, there are ways of handling that by introducing an appropriate work conjugate for that, what we call as the m subscript omega, or the pi moment. Similarly, you can do that in this situation as well, but that's a bit asking too much. And again, as I said, if you want to compare with the literature, the main thing that you can compare with at this level is the Timoshenko theory, and the Timoshenko theory does not involve these primes. Instead, it involves, instead of 4 variables here, 6 variables, by introducing 2 additional variables, 2 gamma 1 2 and 2 gamma 1 3, the transverse shear strain measures. So, is there a way that we can put this or force this into that particular form, 2 gamma 1, involving not only the epsilon bars but also the 2 gamma 1 2 and 2 gamma 1 3. And again, epsilon bar itself might take a different meaning once you go there. Remember that epsilon bar is defined as epsilon subject to 2 gamma 1 alpha equal to 0. In other words, the transverse shear deformation information is contained within the warping rather than as a 1D variable, because it is in reality not a degree of freedom. It is a, even when you introduce 2 gamma 1 alpha, it is an artificial degree of freedom that you are trying to introduce just to force your asymptotically correct solution to be in that particular form. So note that this I already mentioned, the classical 4x4 stiffness matrix that you have as A over there, accounting for initial twist and curvature. So if you look at all the additional terms that you have over here, they all involve a subscript R over here, which means that all of these modifications that were done to the S bar matrix, the 4x4 S bar matrix, were because of the initial twist and curvature. So that is a fact to be observed in the additional terms. So how do we go about transforming this to a generalized Timoshenko model? This is done in more detail in your book. I'm not going to all the details, but just giving an outline of how it is done. So the previous slide, this is the asymptotically correct refined theories energy that we had for unit length. The strain energy density is asymptotically correct. You can verify that. apart from the classical terms, now has an A bar squared term. It's quite obvious because it is quadratic in the strains and therefore the warping, and the additional term in the warping we took was of the order of A bar, and therefore you got an A bar squared correction, which is what is included within this. Now this in turn depends on epsilon bar prime, that is the trouble that we talked about earlier. There is an escape route. One way is to use the 1D equilibrium equations, which we are going to derive after the break. So that 1D equilibrium equations can be used to eliminate the epsilon bar prime in favor of the new variables. The new variables are the ones similar to what Timoshenko himself used, namely the 2 gamma 1 alpha. And the hint is for isotropic beams, of course, Timoshenko incorporated transverse shear using separate 1D generalized strains, the transverse shear strains. So what we will do is, we will extend that. What he did was for isotropic beams, but for composite beams, we can do a similar kind of a thing. And because one of the reasons is, of course, the difficulty in handling the boundary conditions. Not impossible, but difficult. The other is the need to compare with existing literature. And the third is that the composite beam theories with gamma 1 alpha have been shown by other people in the literature to enhance the predictive capabilities compared to the zeroth order solution. So that means that by using that, even though what you would have is not asymptotically correct, it is close to being asymptotically correct, but still the results would be better than using the classical theory alone, that is basically the zeroth order theory that we derived earlier. So that is one of the reasons there. Gamma and alpha exhibit enhanced predictive capabilities for special cases, not for the general case, and therefore we choose this particular approach. So the modified model that we develop is therefore called as generalized Timoshenko model, because it's based on Timoshenko's variables, but it's generalized in the sense that it is derived from the asymptotically correct theory, and also it does not make all of the ad hoc assumptions which Timoshenko himself made in terms of the kinematics. He only allowed going from the Euler-Bernoulli approximations to the Timoshenko model. He only let go of the normal, no longer required to be normal. The other approximations continue to remain, and that's why you have issues. Whereas here, we will be able to force this to be like Timoshenko, behave like a Timoshenko-like model without having to make any of those kinematic assumptions. Modified model only has the same form of the strain energy as the Timoshenko's original model. In other words, you will have 6 strain measures instead of 4. There are 2 additional ones being 2 gamma 1 2 and 2 gamma 1 3. The transverse shear strains, again functions only of x1. And a modified model does not restrict the kinematics in any way. So all possible deformations still included in the modified model, because remember that it is based on this solution, which in turn allowed for all kinds of deformation. First of all, it allowed for as large as you want displacements of the cross section, average displacements of the cross section, average rotations of the cross section. These were allowed to be as large as required, and in addition you allowed for warping in all the 3 directions, and that is also included within this particular theory. In that sense, all possible deformations are still included in the modified model. So we want to go from the asymptotically correct refined model to a generalized Timoshenko model and do it as accurately as possible, knowing fully well that this is not asymptotically correct. So how do we do that? All that we have to do is set an expression for the energy per unit length of this, and expression for energy per unit length of this, which we already derived, subtract the 2 and basically minimize that. So that is easier said than done, because of the fact that this involves derivatives with respect to x1, whereas this involves 2 additional variables. So first of all, we have to relate those 2 additional variables to the already existing variables, because we know that those additional variables are not really degrees of freedom, they are dependent on the existing 4 degrees of freedom. So how do we bring about that relationship, and then how do we minimize the difference between them? That is what we need to do. So use known information about the models. So the strain measure definitions in the asymptotically correct refined model that we used for this derivation if you remember from the previous example as well, is by using the triad TI. Okay, so where the T1, T2, T3 in the deformed configuration was introduced such that T1 is tangential to the deformed reference curve, that is the big R. So that's basically why we really didn't need to explicitly include the 2 gamma 1 2 and 2 gamma 1 3. Of course, the reason why we don't have that is basically because if you go to the so-called phantom step of the variation asymptotic method, where you can deal with all 3D quantities and then use the variation asymptotic method, which we didn't do there, which Berdichevsky has done in some of his initial papers of the VAM. There you would see that only 4 degrees of freedom were extracted, and therefore we basically stepped on from there on to use only those 4 degrees of freedom, and that became quite convenient. On the other hand, if you want to explicitly introduce those artificial additional 2 degrees of freedom, 2 gamma 1 2 and 2 gamma 1 3, instead of dealing with a triad TI, we have to deal with a triad BI. And this we have seen earlier also in the beam kinematics. We have given in various simplified examples. We have shown that we can introduce the V1, V2, V3 in such a way that it is the overall rotation that is taking place of the cross section, and therefore explicitly 2 gamma 1 2 and 2 gamma 1 3 are contained as coefficients of B2 and B3 terms when you are expanding out the position vector of any point, arbitrary point in the cross section, or for that matter a point on the reference line. So that is basically eventually going to lead to a matrix like this. Instead of the S bar matrix, which was a 4x4 matrix, you have an S matrix, which is now a 6 matrix, where you have additional rows and columns in the second and third places, as you see, associated with gamma 1 2 and gamma 1 3, and in turn corresponding to the work conjugate would be the F2 and F3, the shear forces. So with this, we will complete the cross-sectional analysis. We'll take a break of about 5 to 10 minutes, and then we will resume with the geometrically exact 1D analysis, how to get the equilibrium equations. And with those equilibrium equations, we will then finally summarize all that we have done through the course, show you where each one of these fits in and how we would actually apply it to any beam problem that you might have. Thanks.